We will now take up the problem number 2, which says a block of mass 2 kilos is tied to the end of a string which passes through a hole inside the table as shown. Initially the block is at A, moving in a circular path at 4 meter per second. Here it is moving at 4 meter per second. VA. Now the string is pulled from below so that it reaches the point B, moving in a smaller circle of radius OB, which we can say OA and OB both have been mentioned, at 6 meter per second. Calculate A, the work done by the tension in the string. As you pull it, as anybody pulls it, he feels that there is a tension. That tension is actually making it move. Actually, it is moving in a spiral path that has not been shown. It was moving initially in a circle of larger radius. If now it has to move in a circle of smaller radius, it has to get displaced from one point to another. And the actual path has to be a spiral path. So actual displacement is very difficult to find. So let's see how to find the work done. So we have to find out the work done by the tension in the string. That is the first part. Second part is very easy to do, very direct. The tension on the string at points A and B. Alright. So we will answer this question in such a way that we will answer part B first. So that will allow us to see whether the tension is constant. If the tension is constant, that will enable us to apply the force times displacement rule. Is it possible in the first place? Let us find out. First of all, what is the tension at A? Tension at capital A. TA is the only force. The tension at this point is the only force acting on it. Only unbalanced force, and that force equals mass times VA square divided by RE, or M VA square, which is centripetal force, divided by OA. The mass of the object is 2 kilos. OA VA, the velocity at point A, is 4 meter per second. 4 square divided by OA is 3 meter. So 3 meter. So you get 2 16s are 32 by 3 Newton, which is approximately 10.67 Newton. Let us find out the tension at point B. At point B, the tension TB is again the centripetal force acting on the block. So again it is mass times VB square divided by OB. So 2 times VB square, which is 6 square, divided by 2 now. The radius has reduced, 2 and 2 cancel out. 6 squared is 36 Newton. You can see that the tension has increased from as low as 10.67 Newton to as large as 36 Newton. So therefore the force, the tension force, is not a constant force. So we cannot easily find the work done by the tension force by simply multiplying the tension times displacement. 2 things are not known in the first place. One is the displacement itself is not known, because we never know how it has moved from point A to B. Of course there is a spiral path, that's all we know. But the tension force itself is not a constant force. So therefore we can't use the ordinary or elementary formula for the work done. W is equal to F times S, or F times S times cos theta. Sometimes something else must be made use of in order to find the work done by the tension, and that is nothing but the work energy theorem. So work energy theorem says the only force that does the work here, which is tension force, that is equal to the change in kinetic energy between A and B. B is the final point, you see. So kinetic energy at point B is final kinetic energy. The kinetic energy at point A is the initial kinetic energy. So therefore work done by the tension force is half mVb square minus half mVa square, that is half times mass is 2 kilos. Vb square Vb we have already found here, 6 square minus Va square, which is 4 square, 2 and 2 cancel out, 6 square 36, so you get 20 joule. So this is the answer for the part B and this is the answer for part A. Now we shall take the problem number 3. The problem number 3 says a force acts on a body of mass 2 kilos along the positive x-axis. The body moves along the x-axis. If the force is varying with x coordinate according to F, which is a function of x, 3x square plus 4x plus 1, where F is in Newton and x is in meter. A. Calculate the work done by this force when the body moves from x equals 0 to x equals 2 meter. B. If the body has a velocity of 2 meter per second at x equals 0, what is its speed at x equals 2 meter? Assume that the above said force is the only force acting on the body. So let us now understand what is given in the question. You have this as the positive x-axis, this is the origin, and now the body starts from here moving with initial velocity at x equals 0. It is stated to be moving at 2 meter per second. Now thereafter the force acts, which is not a constant but is a function of position coordinate x, and how it exactly varies is given by the formula here. So when it moves from 0, x equals 0 to x equals 2 meter, we have to find out how much is the work done by this force. So if initial point is A, final point is B, we got to find out what is the velocity V. So there are two parts here to do to answer. One is we have to simply find the work done by this force. Second, how much is the velocity gained at point B at x equals 2 meter. So we will answer it. Solution. We know work done by a force along the straight line is simply given by integral of f dx, fx ds or f of x dx, whichever. So it is given f, or which you can also write as f as a function of x into dx. Previously we adopted a formula of this kind. F of x is 3x square plus 4x plus 1 dx. Now the displacement is from x equals 0 to x equals 2. It is a simple integration. So integral of 3x square dx between 0 to 2 plus integral of 4x dx between 0 to 2 plus integral of 1 dx or simply dx between 0 to 2. And here it is very easy. You see 3x square integral of 3 comes outside, x square dx between 0 to 2 plus 4 comes outside, integral of x dx between 0 to 2 plus here you can simply write integral of dx between 0 to 2. Next step, you can easily see 3 times integral of x square is x cube by 3 between 0 to 2 plus 4 times integral of x is x square by 2 between 0 to 2 plus integral of dx is x between 0 to 2. So 3 and 3 cancel, 2 1s are 2 2s are. So upper limit 2 cube minus 0 cube plus 2 times upper limit 2 square minus 0 square plus upper limit 2 minus 0. So very easy. Here you get 8 plus here also you get 8 plus 2 and ultimately you get 18 joules. So 18 joule is the work done, total work done by this force. So integration is something you need to know. I hope in second year PUC you have been taught enough of integration. So now you have to remember a little bit elements of it, if not very complicated integration. Integrations are simpler here. So we will answer now part B. Part B says, if the body initially had a velocity of 2 meter per second, what was its velocity at x is equal to 2 meter? That means initial velocity is 2 meter per second. We would like to know final velocity. It is known that the mass of the body is 2 kilos. So to be able to find the kinetic energy, the velocity V, we know by work energy theorem, work done by this force is change in kinetic energy kf minus ki, that is half mv square minus half mu square wf. Left hand side, work done by the force, we have already found it to be plus 18 joule. So 18 equals half times m is 2 kilos, v square is unknown, minus u square is 2 square. So you find 2 and 2 cancelling out. So v square happens to be 18 plus 4, which is 22, or v is square root of 22 meter per second. And actually we are done with the problem. If you have the calculator, you can find the exact value of this. This is the answer for the second part, and this is the answer for the first part. Next, we will go to another problem here. Next, we shall consider the fourth problem for this chapter. It says a small body slides down on a smooth track from point A. It starts from rest here. As it slides, what are its kinetic and potential energies at B, C, and D? And what are its speeds? At these points it will be moving with different speeds. What are the speeds? At point B, VB, at point C, VC, and point D, VD. How much? That we have to find out. How long does it take for the body to land at F? That means from D to F. How long does it take? We have to find out the time. And finally, how far from E horizontally will the body fall on the level ground? That means we want to find out this distance Ex. So these are the requirements from this question. So we'll answer the first part very easily. So we find that here the total energy, here it was at rest, so therefore the potential energy was mg HA. The kinetic energy is 0 because it is at rest. So total initial kinetic energy is 0, or point A kinetic energy is 0. Potential energy is mg HA. M is not stated, so we can take the mass of the body of mass 2 kgs. So mass is 2 kilos, so 2 times 10 times HA, which is 10 meter, so you get 200 joules. So initial total mechanical energy at point A is kinetic energy plus potential energy, which is 0 plus 200, which is 200 joule. So we'll find out the potential energies at B and D. So we'll probably draw table wherein we'll find kinetic energy on one side, potential energy on other side, or rather potential energy on one side, kinetic energy on the other. At B, C and D. Now potential energy at B, very easy. Potential energy at B is mass times acceleration due to gravity, 2 times 10 times 8. So you get 28 160 joule. So what is the kinetic energy then? Kinetic energy at point B is total energy minus the potential energy. You know, total mechanical energy is constant because there is no friction, it is a smooth track. All through there is no change in mechanical energy. If the total mechanical energy here, which we found as 200 joule, that 200 joule must remain the same everywhere. So what really happens is that as it is climbing down, the potential energy decreases, but the kinetic energy increases. So kinetic energy is always total minus the potential energy. So potential energy is stated to be 160. So 200 minus 160. So you get 40 joule. So that is a kinetic energy. And then potential energy at C, which is mgh. The height here is just 2 meter. So 2 times 10 times 2, so you get 40 joule. So what is the kinetic energy at point C? Kinetic energy at point C is E minus UC, that is 200 minus 40, you can see 160 joule. Then finally at point D, potential energy at point D is mgh. M is 2, G is 10, H is 5. So you get 100 joule, and then kinetic energy at point D is E minus UD, that is 200 minus 100, so 100 joule. So you can see at all points the total energy 40 plus 160, 100 plus 100, 160 plus 40, total is 200 joule. So we can also find the speeds at the respective points. This is the answer for part A. Answer for part B we can find out by extending this table. So the speed at point B, which can be found by KB is equal to half mvb square. So KB equals 40, half times m is 2 times vb square, which we do not know. So therefore vb square becomes 40, or vb equals square root of 40 meter per second. Then Kc is already known here. Kc is equal to half mvc square. So Kc is known, 160 equals half times 2 times vc square. 2 and 2 cancels out. So vc is equal to square root of 160 meter per second, or you could write 4 square root of 10 meter per second. Likewise, this could have been written as 2 square root of 10 meter per second. And Kd is half m Vd square, which is Kd is 100 equals half times mass is 2 into Vd square. 2 and 2 cancels out, so you get Vd equals 10 meter per second. Yes. So we find that at point D, at this point, the object, the body is moving at a velocity of 10 meter per second. And now we know for any horizontally, projectiles, the velocity in the horizontal direction remains the same, meaning horizontal velocity always remains at 10 meter per second. Vertical velocity, initial velocity is 0. So this is equivalent to a single particle falling freely under the action of gravity. So how much time does it take to fall this height? This height is already 5 meter given. That time is given to be square root of 2h by g. And we will answer in so doing the part C. That is 2 times h, which is 5 divided by g, which is 10. 10 by 10 is 1. So square root of 1 is 1 second. So it takes 1 second for the body to fall freely under gravity from D to F. So last part we will answer how much displacement has this undergone along the horizontal, meaning how much is capital X, how much is EF. That is given by horizontal velocity, which remains constant, times the time taken. Displacement is velocity times time taken. Displacement velocity is 10 meter per second, which we found, times 1 second, so 10 meter. Now we shall consider the last topic under this chapter, which is power. We have two types of power. One is average power and one is instantaneous power. We'll come to both of them. To understand the reason for it, or reason for defining such a quantity, let's consider a pitcher or a pot being used to lift water or haul water from the well. So you see, the water level is fixed, so therefore this fellow is going to sink the pot by a height h. And after he sinks it, he pulls it using the rope, he pulls it. As he pulls it, he would have done a work of mgh, and it can't change. M is fixed, mass of the water inside it and the pot, m is fixed, g is fixed, h is fixed. However, he can choose to pull the rope at different times. He can do it slowly, in which the time taken is very large, or he can do it very quickly, in which time is very small. You often know that the quicker he pulls it, or you do it, the more strain or more exhaustion you feel. Why is it so? Because you are expending more power. In both the cases, work done may be the same, but the time being different, the power is different. So the average power which we define, P average, P bar, is simply the total work done divided by total time taken. total work done divided by total time taken. In this particular case, for example, average power is mgh by T. You can easily see as T decreases, power increases, more power. If T is more, P is less. The rate at which the power work is done, which is called instantaneous power, or simply power from now. Instantaneous power or simply power is the rate of doing work dw by dt. So you can easily see that work is dw is f dot dr, and therefore dw by dt is f dot dr by dt. dr by dt, rate of change of position, is the velocity, so f dot v, and therefore we can easily conclude the fact that the instantaneous power is the dot product of the force and the velocity. Or going a step further, we can write instantaneous power is fv cos theta. Or if theta equals 0, in other words, the force acting on the object and its velocity are in the same direction, then theta equals 0, cos theta equals 1. So the maximum power is going to be delivered when the force is parallel to the velocity, and which is simply force times the velocity. So you can see power is the rate of doing work, and it can be understood in a variety of ways too. Rate of doing work or rate of change of kinetic energy. So instantaneous power can also be written as rate at which the kinetic energy changes, or the instantaneous power can be defined as rate at which the potential energy changes, or instantaneous power is the rate at which the total energy changes, and so on, in addition to the rate of doing work dw by dt. And it's very easy, dk is in joule, time is in seconds, so joule per second is the common unit for all the types of work, whether it is instantaneous or average. So the joule per second is called watt, and therefore 1 watt is 1 joule per second. So 1 watt is 1 joule per second. Next we will take up the last problem in this chapter. It says an object moves in the positive x direction under the action of a force which is given to be F, which varies with the velocity Vx as shown in the figure. A. What is the instantaneous power when Vx is 10 meter per second? When Vx is, this is 4, 8, 10. When it is 10, what is the instantaneous power we have to find out? Second, what is the average power between x equals 0 to x equals 20 meter? X equals 0 to x is equal to 20 meter. So we have to find the average power. So let's answer both of the questions now. Part A, very easy. At x equals Vx equals 10 meter per second, when Vx is equal to 10 meter per second, Vx equals 10 meter per second, the force is given to be 10 Newton. So we know the instantaneous power is force times velocity. Force is 10 Newton times velocity is 10 meter per second. So you get 100 watt. Very, very easy. The second part, B, is not very easy, I would say. We have to find out the average power. To be able to find the average power, since the force is varying with Vx, the velocity, we can write the power over a small velocity change dVx is F times dV. So total power or average power is integral of F dV. The integral of dV is nothing but area under F versus V graph. So between, of course, V is equal to 0 to V equals 20 meter per second. And it is very easy to find the area. So this entire shaded region will give you the total power or average power between 0 to 20, and that is the area under the two segments. One is the rectangle, one is the trapezium, which we will mark here in blue color, and in pink color this is a triangle. So we have to find this area and add this to this triangular area. So the total area, which is the total work done, is area under the trapezium half times the sum of the unequal sides, which is 14 plus 12, 14 plus 12 times the perpendicular distance, which is 10, plus the area under the triangle, that is half times base, is 4, 4, 4, 12 times height, which is 10. So you can see that 14 plus 12 is 26, 260 by 2 is 135, 130 plus 60, you get 190 watt. So the average power between the starting Vx is equal to 0 to Vx is equal to 20 meter per second is 190 watt. Thank you. I hope you have enjoyed this video. Have a nice day.